Nakamura. I'm project manager of Cryogenics History in Mayekawa, Japan, R&D Center. Mr. Yambone introduced the major Mayekawa information already. I would like to present you about our new technology. At the first, I would like to introduce about cryogenics history. Mayekawa business target range is wide, from 200 degree minus 270 degree. Today's presentation is focused on the cryogenics field. 40 years ago, I started providing helium compressor utilizing helium liquefier. Recent 10 years, I have developed liquid nitrogen cooling system and Turbo-Brayton refrigerator for superconducting cable. Then, I should explain the superconducting cable technology and cable project in Japan. Normal conductor, ohmic heating is occurred material resistance. But superconductor is no heating based on resistance becomes zero under the critical temperature. Major superconductivity application, MRI and maglev. Superconducting material of high critical temperature we call HTS, high temperature superconductivity. One of major application of HTS material is transmission power cable. HTS cable could be transmitted to large capacity and with more compact size and lower voltage. Furthermore, transmission loss of HTS cable is reduced to 77% compared to conventional cable. It means the superconducting cable is could be CO2 reduction. This is outline of superconducting cable project in Japan. Superconducting cable, this is the demonstration test in real grid. Superconducting cable is connected to Tokyo Electric Power Company's network. It means if HTS cable is system down, a part of the city is blacked out. High-risk project. We had implemented this project for 10 years. We have two-phase project. First phase project, we verified HTS cable performance and reliability. In parallel, we had developed new refrigerator. After slide, I described the new refrigerator. Second phase, we verified the reliability and operation new refrigerator. HTS superconducting cable system is located in substation of Yokohama. This is layout in Yokohama. This is layout of a superconducting cable system. This is a cut model of superconducting cable. Superconducting cable is cooled liquid nitrogen. Liquid nitrogen is flowed at this area and circulated superconducting line like this. This is a cooling system flow. Liquid nitrogen is circulated by centrifugal pump and cooled refrigerator to keep the subcooled state of nitrogen. First phase project, we used Stirling type refrigerator. Stirling refrigerator compressor is reciprocal type as a piston. Stirling type, cooling capacity of Stirling type a little bit small. So we had 6 unit Stirling refrigerator. I successed the long-term operation the superconducting HTS cable system. We verified the reliability and long-term operation stability superconducting cable. Then, Stirling refrigerator has a technical issue. First, low efficiency. Average COP of 1 year and 6 units is 0.05, but our target is 0.1. Secondary, Stirling refrigerator short maintenance interval of 8,000 hours as a piston type compressor. Requirement maintenance interval for power grid equipment 30,000 or 40,000 hours. 8,000 is very short. Then we challenge development of high performance refrigerator. Requirement performance of refrigerator for HTS cable. First, large capacity. Requirement cooling capacity HTS cable practical use is 20 kilowatt, but the cooling capacity of 20 kilowatt a little bit large. That's our first challenge. So I decide the first target of 0.5 kilowatt. To achieve cooling capacity 5 kilowatt, we chose the reverse Brayton cycle refrigeration system. Secondary, high efficiency. If COP of cooling system is 0.1, HTS cable loss is reduced to 50% compared with conventional cable. COP is 0.1, a big challenge for us because basically cryocooler as a Brayton cycle, another type, COP is 0.05 or 0.06. 0.1 is very big, very difficult value. To achieve COP 0.1, we developed high-performance turbo compressor and expander. Finally, high reliability. I said already, maintenance interval for power grid equipment required 30,000, 40,000 hours. To achieve maintenance interval of 30,000, 40,000 hours, we used the magnetic bearing. This is the system flow of Turbo-Brayton refrigerator we developed. This refrigerator consists of 3 turbo compressor and 1 turbo expander. Another after 3 aftercooler and 2 heat exchanger. Heat exchanger is aluminum plate heat type. This is impeller of compressor and expander. first stage, second stage, three-stage compressor and expander. And this is first stage and second stage compressor. First stage and second stage impellers set in the one shaft and both sides. And one motor is operated shaft and impeller. A third compressor and expander is almost the same structure. We used one shaft and two impellers, perfect contactless by using magnetic bearing. This is the result of factory test. We achieved a COP 0.1 at 77 Kelvin. This value is highest efficiency in the world, another cryogenics refrigeration system. We achieved the performance of refrigerator and we achieved the development of new refrigerator. Then we moved this refrigerator to substation of Yokohama. We changed the refrigerator from Stirling type to Turbo-Brayton refrigerator like this. This is the layout of cooling system. This is the Turbo-Brayton refrigerator we developed, and this is the reservoir tank of 1,000 liter. This rod is a receiver of pump. This is the centrifugal pump. We operate this system of 40-60 hours. This is the result of second phase operation in real grid. Green line, the heat loss of HTS cable, and the red line, outlet temperature of refrigeration, liquid nitrogen temperature, and the flow rate, blue line is the flow rate of liquid nitrogen, and the pink line, the pressure in reservoir. We success the long-term operation. This operation is very stability and no big trouble for over 1 year. This is the result of COP. Turbo-Brayton refrigerator is affected the temperature, cooling temperature, water temperature of after cooler. In Japan, winter is very cold. Then temperature of cooling water after cooler is lower. Then COP is more higher compared to summer's value. Basically, Turbo-Brayton refrigerator cooling capacity controlled use rotational speed control. But the rotational speed control is COP is change the each cooling capacity. Then we used another method. We used mass flow control. Mass flow control. Flow rate of coolant now is neon gas. Neon gas is controlled to make the each cooling capacity. This method could be kept highest COP. We check we check the COP before and after long-term operation. This value is almost the same. It means this refrigerator performance is kept at long-term operation. After project, I improved this refrigerator. Demonstration test, to achieve the COP 0.1, Turbo-Brayton refrigerator size and footprint is more larger, very big. Then we improved this refrigerator, more compact size and more easy operation. Okay, so this characters of this refrigerator, oil-free and coolant, natural neon gas or liquid nitrogen gas. It means very green. Let me conclude. Today, I introduced our new technology, superconducting cable or Turbo-Brayton refrigerator we developed. We achieved, we successed the development of Turbo-Brayton refrigerator, and we confirmed the reliability and stability of operation this refrigerator. And after now, we provide this refrigerator for superconducting customers worldwide. Today, thank you for opportunity my presentation, and thank you for attention. Thank you for attention.